Hey guys, it's Luke, and today we're going to talk about the synthesis of enantiomerically enriched or pure compounds. So, as in the last video, we saw the ways we can determine what isomer we've got. In this case, we can determine, we can make sure that we make the certain product. So, we're going to split this up into three different parts in three different videos. It's chiral pool synthesis, chiral reagents, and chiral auxiliaries, and they're going to be three different topics. This chiral pool one's going to be a little bit shorter than the other two. So, chiral pool synthesis, what is it? We'll use readily available natural occurring compounds whose stereochemistry is already defined, so we already know their stereochemistry effectively. So, for example, we can use amino acids. So there's a threonine there. Multi-step reaction, we can form pretty much a peptide bond in a circular format, in a cyclic format. Just need to remember that we form the cyclic bond there, sort of like an SN2 reaction, as shown in the previous step. Obviously, one comes in, one goes out. As you can see, we've got the bot group protecting our amine group as well this time. And once again, another multi-step shows the stereochemistry there, facing towards us for this group that we've made, and we're unprotecting this step here. So we can also use carbohydrates and sugars, for example glucose. 5-step process takes us to this epoxide, or this diepoxide, a diol column ketone, and then from that we get this selectivity here, which allows us to know the stereochemistry as we're going through it, because we've got that same stereochemistry just there as well. The problem is, sugars have a lot of chiral information, but they might need to remove the stereogenic center. The stereogenic center is just where you can basically change two groups around an atom or molecule, and once you've done that, you make a stereoisomer of it. Finally, you can use terpenes as well. Now, terpenes are these things here. As you can see, we've starred this chiral center here first. We then make this compound in a multi-step reaction. We've labelled these two centers. In this case, once we do that, we draw a sort of chair conformation here, after reacting it with BF3 and ETO, or an aldol, any sort of aldol. We get this product, very hard to draw, or fairly hard to draw anyway. Obviously that just cyclizes to here pretty much, and then this part is from our former benzene ring, I believe. And then finally, with another multi-step reaction, is that we can see our chiral, we can see our initial center there, which is what we started with. So that should be effectively there as well, I believe. But yeah, that's chiral pool synthesis. It's limited because a suitable available starting material must be recognised in the final product, which is that there, from there to there. And we've still got this sort of benzene ring as well. And the functionality is often removed during the synthesis over time, so obviously the longer it's going, the functionality is decreasing, which is making the molecule that you're using a little less active and a little less useful to you. But that's basically chiral pool synthesis. I know there's not much to know about the mechanisms and stuff. You just need to sort of reproduce these reaction schemes just to show how these things work. There's not many curly arrows, but next time there's going to be some very important things on chiral reagents, so it's an important video.